Welcome. Tonight we're not just looking at the night sky, we're travelling through it. Beyond the Moon and Mars lie the true giants of our solar system: Saturn, Jupiter, Uranus, and Neptune. They're not just distant dots of light. Each hides mysteries so strange that even today scientists still debate them. Take Saturn. A spacecraft spent 20 years just reaching it, then orbited for 13 more. In the end, it deliberately dove into Saturn's clouds, burning up as it sent its last data home. Why would scientists destroy a billion-dollar probe? That story is coming. Or consider Jupiter, king of planets. Its great red spot could swallow Earth, and its radiation is strong enough to kill a person in hours. Yet without Jupiter, Earth itself might never have survived. Farther out, Uranus rolls on its side, its poles locked in decades of unbroken day or night. Deep within, scientists believe diamonds rain through the atmosphere, and Neptune, dark, distant, frigid, unleashes supersonic winds faster than anything else in the solar system. It shouldn't be so violent, but it is. As you listen, you'll hear facts that sound impossible, and questions even science can't answer. So don't drift off yet. Stay with me for the tale of Cassini, the spacecraft that became a legend, and in its final moments gave us one last gift before vanishing into Saturn's golden haze. When we finish, tell me which mystery you'd like to explore next. Your choice may shape the journey to come. Long before Cassini's Saturn was already a dream. Galileo, with his crude telescope in the 1600s, thought Saturn's rings were ears. Later, astronomers refined the picture, but the mystery remained: what was Saturn really like beyond the blur? By the late 20th century, we began to reach out. Pioneer 11 flew past in 1979, giving our first close-up view. It showed Titan, the largest moon, had a thick, hazy atmosphere. Voyager 1 and 2 followed in the early 1980s, revealing stunning ring images, new moons, and confirming Titan's dense atmosphere. But they were flybys, quick visits, then gone. Scientists wanted more. They needed a craft that would stay orbit Saturn for years and even explore Titan's surface. That ambition created Cassini-Huygens, a collaboration between NASA, ESA, and the Italian Space Agency. Cassini would orbit Saturn. Huygens' ESA's probe would parachute down onto Titan. Launched in October 1997, Cassini was massive, over 500-600 kilograms, to reach Saturn 1. 4 billion kilometers away, it used gravity-assist 2 flybys of Venus, 1 of Earth, then Jupiter, each slingshotting it outward. This alignment happens only once every 600 years. Cassini made the window, but there was risk. Solar panels wouldn't work so far from the sun, so Cassini carried 3 RTGs, radioisotope thermoelectric generators powered by 33 kilograms of plutonium-238. Reliable, long-lasting, but dangerous. NASA calculated the odds of an accident at 1 in a million, yet if Cassini had broken up in Earth's atmosphere, thousands could have been exposed. The launch succeeded, but the risk shadowed the mission. In one Earth flyby, Cassini skimmed just 100 kilometers above the surface, closer than many satellites. A single miscalculation could have been catastrophic. For nearly 7 years, Cassini cruised through the void, a silent traveller bearing humanity's hopes. On July 1, 2004, it fired its engines and slipped into Saturn's orbit. For the first time, we had a permanent outpost circling the ringed giant, and Cassini was not alone. Strapped to its side was Huygens, the Titan lander. At the right moment, it would detach and plunge into Titan's orange skies. The prospect was electrifying. No one had ever landed on a world so distant, with conditions so alien. Would Titan be mud ice or ocean? No one knew. The mission was set. Cassini would orbit Saturn, exploring rings, moons and magnetosphere. Huygens would touch Titan, offering our first direct glimpse of its surface. Together they would rewrite Saturn's story. Yet even at this hopeful beginning, there was a shadow. The silent plutonium aboard Cassini was a reminder of the stakes. One mistake could have changed Earth's fate. For now, though, Cassini was young, a gleaming machine entering Saturn's gravity well, for the first time, cameras ready, instruments alive. Humanity's eyes and ears had arrived at one of the most beautiful and baffling worlds in the solar system. Cassini entered Saturn's orbit in July 2004, and for the first time a spacecraft was staying, not just passing by. Saturn was no longer a blur, it had become a neighbour. Almost immediately, Titan drew attention. No telescope could see through its orange haze. On Christmas Day 2004, Cassini released the Huygens probe. 3 weeks later, Huygens plunged into Titan's atmosphere. Parachutes deployed instruments measured winds, temperature and chemistry, and cameras captured river channels, hills and coastlines. Against all odds, it landed safely on frozen ground mixed with hydrocarbons. Its batteries lasted for over an hour, sending humanity's first direct images from a world over 1 billion kilometers away. Titan turned out to be the most Earth-like place ever visited, except its lakes and rivers were filled with liquid methane and ethane. Cassini itself orbited for 13 years, every flyby carefully planned. It skimmed close to moons like Enceladus, then soared high for global views. The rings once thought simple came alive, ripples, waves, and propeller-shaped gaps carved by hidden moonlets. Dust ice and gravity danced under the guidance of shepherd moons. Enceladus, a small icy moon, became one of Cassini's greatest discoveries. In 2005, plumes of water vapour and ice erupted from its south pole, some feeding Saturn's E-ring. Cassini flew through the plumes, detecting water, organic molecules and salts. These were the ingredients of habitability. Suddenly, Enceladus, a body only 500 kilometers wide, was seen as a potential home for life. Saturn itself proved equally strange. Its atmosphere showed bands and colossal storms. At the North Pole, Cassini revealed a vast six-sided jet stream, the hexagon. How could nature carve such geometry into gas? Its magnetosphere added more puzzles, linking planet rings and moons in unexpected ways. Measuring Saturn's day length proved maddening. Its magnetic field was aligned almost perfectly with its axis-defying theory. Only by studying ripples in the rings could scientists estimate its rotation. Cassini's long residency was not routine but a chain of surprises. Each discovery opened new questions, and beyond the science, the spacecraft became something more than a machine. Year after year, it endured radiation, cold, and distance, sending home images that became works of art. Saturn backlit by the Sun Titan's orange globe, Enceladus's icy fountains. Cassini felt less like hardware and more like a companion, an explorer at the edge of human reach. As the years passed, Cassini became more than a mission. Each orbit added a new piece to Saturn's puzzle discoveries that reshaped how we saw the planet and its moons. One hallmark was Cassini's ability to capture beauty as well as data. Sometimes it slipped into Saturn's shadow and looked back toward the Sun. The rings glowed like stained glass, and Earth appeared as a pale dot tucked into their curve, a reminder of how small and yet connected we are. Over 400,000 images came down during its lifetime, many stitched into movies showing moons drifting past rings, shadows sliding across clouds and auroras glowing at the poles. The moons became central to Cassini's story. Mimas, scarred with a giant crater, looked like the Death Star. Iapetus, half bright, half dark, was a riddle. Titan revealed lakes and seas of methane rainfall from hydrocarbon clouds, and rivers etched across its surface, eerily Earth-like but alien. And Enceladus stole the spotlight. Each flyby through its plumes revealed salty water organics, even signs of hydrothermal activity below the ice. It was as if an ocean, sealed beneath kilometers of crust, was venting its breath into space. The possibility of life there no longer seemed like fiction. Cassini also showed Saturn's rings weren't eternal. Material was raining down into the atmosphere, hinting the rings may be only about 100 million years old. In cosmic terms, that's young. We may be alive at a lucky moment seeing Saturn in its most spectacular form. The weather added more drama. From a distance, Saturn looked serene, but Cassini found storms that raged for months. In 2010, a colossal outbreak encircled the entire planet, something never seen before. The spacecraft built for 4 years lasted 13. Instruments kept working. Fuel lasted longer than planned. Each extension was a gift and each brought surprises, but Cassini had no way to refuel. Its thrusters would one day run dry, leaving it unable to aim its antenna at Earth. Letting it drift was risky. If it crashed into Titan or Enceladus Earth, microbes could contaminate those worlds. The mission needed an intentional safe ending. By the mid-2010s, Cassini was part of the human story. Children who watched it launch were now adults. Scientists had devoted decades of their lives. And so the team chose a finale worthy of its journey. Cassini would dive again and again between Saturn and its rings, a region no spacecraft had ever entered. Each pass would bring data impossible to get otherwise, and at the end it would plunge into Saturn itself, transmitting until the last possible moment. For now, picture Cassini circling faithfully Saturn's rings, arching like frozen rivers of light below. A solitary explorer far from home, still alive with questions. By 2016, Cassini had orbited Saturn for over a decade, far beyond its expected lifetime. But fuel was running low. Without thruster control, it would eventually lose contact with Earth. The team faced a choice: let it drift silently, or end with purpose. They chose the latter. Engineers designed a bold plan. Instead of keeping Cassini at a distance, they sent it closer than ever before. In late 2016, Cassini began 20 ring-grazing orbits, skimming just outside the F-ring, photographing moons like Pandora and Prometheus as their gravity sculpted icy ripples. On April 22, 2017, Cassini shifted onto its final path, the grand finale. For 5 months, it would dive between Saturn and its innermost rings, through a gap only 2,000 kilometers wide. No spacecraft had ever ventured there. The risk was immense. One collision could end the mission instantly. Yet the rewards were extraordinary. Cassini mapped Saturn's magnetic field with unprecedented precision-measured ring material, and even sampled icy dust raining into the atmosphere. The images were breathtaking: Saturn's cloud tops, glowing gold, and cream rings arching overhead, with grooves and waves etched by gravity. From Cassini's view, the planet filled the sky. Close passes also brought striking discoveries. By tracking tiny shifts in Cassini's orbit, scientists weighed the rings directly and found them less massive than expected, perhaps only 100 million years old, formed around the time of Earth's dinosaurs, and they will not last forever. Material steadily falls inward. One day, Saturn may be bare. The finale also revealed Saturn's interior. Data suggested a fuzzy core where rock and ice blur with hydrogen and helium instead of forming a sharp boundary. Each dive was a brush with danger. Cassini sped past Saturn at over 120,000 kilometers per hour, threading the invisible gap again and again, returning science each time. To mission planners, it was more than a probe. It was an explorer taking risks, not for survival, but to give. For scientists, the finale was both thrilling and bittersweet. Every orbit was a step closer to the end. The final plunge was scheduled September 15th, 2017. On that day, Cassini would dive into Saturn's atmosphere, transmitting until drag tore it apart. In its last months, Cassini worked harder than ever, mapping auroras, sampling the upper atmosphere, and capturing the most detailed ring images yet. Every bit of data was treated as a farewell gift, and though it was sad, there was pride. Cassini wasn't fading quietly, it was closing its mission with daring a series of acts no spacecraft had ever attempted. By September 2017, Cassini had completed 22 dives between Saturn and its innermost rings. Fuel was nearly gone. Without propellant, it would soon lose control and fall silent. The team refused to let that happen by chance. A deliberate planned end was chosen. The date was set September 15th, 2017. That morning, Cassini would plunge into Saturn's atmosphere, transmitting until its last moment. The sacrifice ensured Titan and Enceladus worlds that might host life would remain uncontaminated by Earth microbes. The night before, scientists gathered in Pasadena. Many had spent decades with Cassini. For them, it wasn't just hardware, it was a companion. On its final approach, Cassini kept its antenna locked on Earth. At over 120,000 kilometers per hour, it pierced the atmosphere 900 kilometers above the cloud tops. Instruments tasted hydrogen, helium, and trace gases. For about a minute, Cassini fought drag holding steady as data streamed home. Then the atmosphere thickened, thrusters strained, and the signal flickered. Moments later, it vanished. Because Saturn is over 1 billion kilometers away, the final signal took 83 minutes to reach Earth. By the time the silence arrived, Cassini was already gone. In mission control, some scientists wept. Others embraced, all knowing the spacecraft had fulfilled and exceeded every goal. Its final act was to return science. Even in death, Cassini continues to teach. Its atmospheric data still provides insights into Saturn's chemistry, magnetic field, and upper layers. Its legacy is immense. Titan's methane lakes, Enceladus's hidden ocean rings that are younger and more dynamic than once believed, and storms that defy expectations. Saturn is no longer just a gas giant, it is a laboratory of physics and chemistry. But Cassini gave more than discoveries. Its images Saturn backlit by the Sun-Earth. A pale dot in the distance reminded us of fragility and wonder. Exploration, Cassini proved, is about perspective as much as data. The grand finale was the perfect end, not silence in the dark, but a final dive into Saturn's golden clouds. Its story inspires new explorers, and its questions remain alive, waiting for future missions to answer. Even after 2 decades of Cassini and Huygens, Saturn remains a world of paradoxes. For every question answered, new puzzles emerged. It often seems as if Saturn delights in breaking the rules of nature. One striking example lies at the North Pole, a massive jet stream shaped like a hexagon. First hinted at by Voyager, Cassini revealed it in detail 29,000 kilometers across each side, wide enough to fit Earth. Unlike the chaotic clouds around it, the hexagon stays fixed, rotating steadily with the planet. Lab experiments can create small hexagons in fluids, but nothing on this scale. Stranger still, the storm changes colour, with the seasons dark in one decade and pale in another. Another riddle is Saturn's day. Rocky planets reveal their rotation with surface features, but Saturn has no surface, only shifting clouds. Normally scientists use magnetic fields, which usually wobble as planets rotate. Cassini, however, found Saturn's magnetic field almost perfectly aligned with its axis, something dynamo theory says should collapse. So researchers tried listening to radio emissions. They pulsed about every 10 hours 40 minutes, but over Cassini's mission this rhythm drifted. Saturn could not actually be changing speed, that would be impossible. Instead, something in the atmosphere or magnetosphere was masking the true rotation. The answer finally came from Saturn's rings. Cassini measured ripples caused by gravity inside them, fixing the day length at 10 hours 33 minutes and 38 seconds. A neat solution, yet the deeper mystery remains: why is the magnetic field so perfectly aligned? Saturn also shines with more heat than expected. A planet so far from the Sun should radiate only what it absorbs. Instead, Saturn emits nearly double. Some of this comes from slow contraction, but not all. One idea is helium rain droplets sinking through hydrogen layers and releasing heat. Another is auroras powered not just by the Sun, but by charged particles flowing between rings and atmosphere. Whatever the cause, Saturn runs hotter than theory allows. And then there are the rings, the planet's iconic feature. For centuries they seemed eternal. Galileo saw them in 1610, Huygens described them correctly in 1655, and telescopes since have admired their icy arcs. But Cassini measured their mass and the rate of material falling into Saturn. The result, the rings are young, maybe only 100–200 million years old. Dinosaurs may have seen Saturn bare. Worse, the rings are fading. Cassini detected icy particles streaming into Saturn's atmosphere like sand through an hourglass. In another 100 million years they may be gone. Humanity then lives at a lucky time, witnessing Saturn at its peak. Future beings may only see a stripped gas giant and wonder what they missed. So Saturn remains a planet of riddles, a storm shaped like geometry, a rotation hidden from view, a mysterious heat and rings that are young and temporary. Cassini gave us answers, but more importantly showed us how much we still don't know. Beyond Saturn itself, Cassini uncovered mysteries among its moon's worlds that refuse to follow the rules. take Enceladus. Before Cassini, it was just a frozen speck 500 kilometers wide. Then Cassini spotted plumes of water vapor blasting from its south pole, some feeding Saturn's faint E-ring. The plumes pointed to an underground ocean warmed by tidal forces. Flying through them, Cassini detected water salt's organics and hydrogen gas signs of hydrothermal activity on the ocean floor. With liquid water energy and chemistry, Enceladus became one of the best candidates for life beyond Earth. And then there's Titan. Cassini's flybys revealed lakes, seas and rivers not of water, but of methane and ethane. Radar traced coastlines and channels carved by methane rain. Huygens, released in 2005, descended through Titan's haze, photographing valleys and icy pebbles, before landing on what looked like a dried lake bed. Titan proved to be alive, with weather and geology reshaped slowly under a dim sun. Titan's chemistry added a final twist. Cassini found complex organics forming in its atmosphere as sunlight split methane and nitrogen. These particles drifted down, coating the surface in dark haze. In many ways, Titan resembles early Earth before biology began. Its lakes are frigid, its air unbreathable, yet it may be a natural laboratory for the chemistry of origins. Cassini also showed that Saturn's system is tightly interwoven. Charged particles spiral along magnetic field lines, from rings into the atmosphere sparking auroras. Dust and ice cycle between moons and rings, blurring their boundaries. Saturn is not just a planet with moons, it is a living system, its parts tied together in ways no one expected. And so the riddles deepen. Why is Saturn's magnetic field aligned in a way theory says is impossible? Why does it radiate excess heat? How did the rings form so recently, and how long will they last? Could life swim in Enceladus's ocean? Could Titan's chemistry hold the key to beginnings? Cassini answered enough to transform our understanding, but left just as many questions behind. Even today, its data is still being analysed, with new discoveries emerging. In a way, Cassini has not stopped speaking. When we see Saturn now, we see not just a planet, but a puzzle storms in geometric shapes, a magnetic field that defies models' heat, without explanation, rings and moons acting as one system. Saturn is not just beautiful. It is an enigma still whispering challenges to science. And perhaps the greatest mystery of all, why Saturn stands out among the giants. Is it truly unique, or have we not yet looked closely enough at its neighbours? Perhaps the next mission, like NASA's Dragonfly to Titan, will bring answers. Until then, Saturn remains the rule breaker of the solar system, reminding us how much we still don't know. If Saturn's rings are its crown, then its tiny moons are the jewels that keep that crown in place. Cassini revealed that many of these small bodies barely known before play a central role in sculpting and maintaining the rings. They are called shepherd moons, and the name is fitting. Like sheepdogs guiding a flock, these moons tug and pull at the icy particles, keeping them in line, shaping the edges and creating patterns that ripple across the rings. One of the most memorable is Atlas. Barely 40 kilometers wide, it looks nothing like the cratered spheres we expect of moons. Instead, Atlas resembles a flying saucer or a dumpling. Its strange shape comes from ring particles coating its equator, piling up like a belt of snow. Cassini's close-up images of Atlas were surreal, smooth ridges circling the middle, giving the impression of something sculpted rather than natural. But it is natural. It is the quiet result of gravity gathering ring dust and ice orbit after orbit, until Atlas looked like a cosmic pastry. Pan is another shepherd moon orbiting inside the narrow Encke gap within the A-ring. Only about 30 kilometers across, Pan also sports a strange ridge of ring material, giving it the look of a walnut. Its gravity clears the gap as it orbits, sweeping out particles and maintaining the channel. Cassini captured Pan in detail, revealing how even such a tiny object can shape the grand architecture of Saturn's rings. Without Pan, the Encke gap would collapse. Daphnis, even smaller, just 8 kilometers wide, lives inside the Keeler gap. Cassini's images of this tiny moon were some of the most dramatic. Though Daphnis itself is hardly visible, its influence is vast. As it orbits, its gravity pulls on the edges of the gap, creating waves, the Arban route gone 820 year. If Saturn's rings are its crown, then its tiny moons are the jewels that hold it in place. Cassini revealed that these small bodies called shepherd moons shape and maintain the rings. Like sheepdogs, they tug and pull at the icy particles, keeping them in line and carving edges and patterns. Atlas, about 40 kilometers wide, looks like a flying saucer. Its odd shape comes from ring particles building up along its equator. Cassini's close-ups showed smooth ridges circling its middle, the quiet result of gravity gathering ice orbit after orbit. Pan only 30 kilometers across orbits inside the Encke Gap. Its gravity clears the gap and maintains it, giving Pan the look of a walnut. Daphnis, just 8 kilometers wide, lives in the Keeler Gap. Though tiny, its gravity raises waves in the ring edges, ripples that stretch hundreds of kilometers. Cassini even photographed their shadows sweeping across the rings as the sun's angle shifted. Beyond these moons, Cassini discovered disturbances nicknamed propellers. Caused by unseen moonlets, they nudge particles aside, leaving twin gaps like blades. Thousands were found hinting at embryo moons that never fully formed. The rings, in a sense, are still trying to create new worlds. The F-ring proved to be one of the most dynamic places. Narrow and braided, it constantly changed. Dense clumps or snowballs formed, broke apart and reformed under the pull of moons like Prometheus and Pandora. Cassini saw streamers drawn out by Prometheus features that later drifted back. Cassini showed that moons and rings are deeply connected. The rings coat moons with ice. The moons sculpt rings by tugging at their edges. Dust and ice shift inward to Saturn, or outward into new structures. It is not a static system, but a living one. Scale makes it even more humbling. Shepherd moons are tiny, yet their gravity ripples across tens of thousands of kilometers. Even a moon the size of a city can sculpt a ring system larger than Earth. Cassini's images of Atlas Pandaphnis and the F-ring were among its most captivating. They looked almost designed saucer-like moons, rippling waves, braided strands of ice. Yet all were natural products of gravity, motion and time. In its final years, Cassini drifted close enough to trace clumps of ice and follow waves in detail. These tiny interactions told big stories: how planets and moons form, how matter organizes itself, and how fragile beauty emerges from chaos. Saturn's shepherd moons remind us the universe is vast but also delicate. The rings are not monoliths, but the sum of countless interactions. Without the small moons, Saturn's rings would look very different, and without Cassini, we would never have seen them in such exquisite detail. Jupiter is the heavyweight champion of the solar system, large enough to fit more than 1/300 Earths inside. Despite its size, it has no solid surface. What we see is atmosphere layer upon layer of clouds shifting in constant motion. Visible to the naked eye since ancient times, Jupiter has been a beacon in the night sky. But telescopes and spacecraft revealed its true face stripes, storms and unimaginable weather. The bands that circle the planet are jet streams moving at hundreds of kilometers per hour. Light-coloured zones and dark belts alternate, each representing a circulation of gas. Their colours come from chromophores, chemicals formed when sunlight interacts with gases like ammonia and sulfur. The result is a shifting palette: whites, ochres and reds. Jupiter's atmosphere is like a thermal map of chemistry rising from the depths. The most famous feature is the Great Red Spot, a storm so large it could engulf Earth. Observed for more than 350 years, it spins counterclockwise in the southern hemisphere, its winds topping 400 kilometers per hour. With no land to slow it, the storm has lasted centuries. But it is changing. In the 1800s, it stretched 40,000 kilometers wide. Today, it's closer to 16,000. Its colour has shifted too, from deep red to pale salmon and back. Some believe it is fading, others that it cycles in size and hue. Jupiter's atmosphere is full of storms. In the 1990s, 3 merged to form Red Spot Junior. Swirls and eddies form where bands meet zones of turbulence larger than continents. It is like watching colliding ocean currents, but with hydrogen, helium and ammonia under immense pressure. Adding to the chaos is Jupiter's speed. The planet rotates once every 10 hours, making it the fastest spinner in the solar system. The rapid rotation flattens its poles and fuels jet streams that carve its bands. Combined with its massive atmosphere, this rotation drives weather systems beyond anything on Earth. Yet the violence has its beauty. The stripes are hypnotic, the colours subtle and shifting. The Great Red Spot could terrify with its scale, but instead it fascinates. To look at Jupiter is to see weather turned into architecture storms that outlast civilizations, and this is only the beginning. Beneath its clouds lie crushing radiation belts, an immense magnetic shield, and a role as both destroyer and protector of worlds. If Jupiter's clouds are its face, then its magnetosphere is its invisible armour and its hidden menace. A magnetosphere is the bubble created by a planet's magnetic field, deflecting charged particles streaming from the sun. Earth has one, and without it our atmosphere would have been stripped away long ago. Jupiter's magnetosphere, though, is in a class of its own. Generated by metallic hydrogen deep inside the planet, hydrogen compressed so intensely it behaves like a metal. Jupiter's magnetic field is the strongest of any planet in the solar system. 14 times stronger than Earth's, it carves out a bubble in space so huge that if it were visible from Earth, it would appear larger than the moon in our night sky. This shield stretches millions of kilometers, enveloping Jupiter and many of its moons. But inside this protective bubble lies a danger. Trapped within the magnetosphere are belts of radiation so intense they would be instantly lethal to humans. These belts are cousins to Earth's Van Allen radiation belts, but far more powerful. Any spacecraft flying too close is bathed in a torrent of high-energy particles. Electronics fail. Instruments short out. Even the hardy probes we've sent like Galileo in the 1990s suffered damage from the invisible storm. Banroot gone 822. If Jupiter's clouds are its face, its magnetosphere is its invisible armour and its hidden menace. A magnetosphere is the bubble carved by a planet's magnetic field, deflecting charged particles from the sun. Earth has one. Without it, our atmosphere would be gone. Jupiter's is in a class of its own. Powered by metallic hydrogen deep inside Jupiter's field is the strongest in the solar system, 14 times stronger than Earth's. It creates a bubble so vast that if visible, it would appear larger than the moon in our night sky. This shield stretches millions of kilometers, enclosing Jupiter and many moons. Inside lies danger. Trapped within are belts of radiation lethal to humans. They are cousins of Earth's Van Allen belts, but vastly stronger. Spacecraft flying too close are battered by high-energy particles. Even Galileo in the 1990s suffered damage from this invisible storm. On Io, Jupiter's volcanic moon, a person would absorb a fatal dose of radiation in hours. The environment is deadly but structured. Io's eruptions blast sulfur and oxygen into space caught by Jupiter's field and whipped into a glowing plasma torus. In ultraviolet, it shines like a cosmic halo-proof. Jupiter creates its own space weather. Auroras blaze at its poles brighter and more energetic than Earth's. Unlike ours, they flare regardless of solar activity. Some are powered by the planet's fast rotation, others are driven by Io itself. As the moon orbits, it drags on magnetic field lines, generating currents that funnel into Jupiter's poles. Imagine northern lights magnified 1,000 times permanent and tied to a volcanic moon. This magnetosphere is both guardian and hazard. It sweeps debris from the solar system, yet makes survival near Jupiter nearly impossible. For spacecraft designers, it is a constant challenge. Pioneer and Voyager passed through quickly. Galileo endured years of radiation damage. Today, NASA's Juno avoids the worst by looping in and out its instruments shielded in a titanium vault. Despite the risks, we keep returning. Jupiter's field is a laboratory for understanding magnetic dynamos, how moons and planets exchange matter, and how radiation shapes systems. Lessons learned here apply across the galaxy, from exoplanets to distant stars. For listeners, such radiation may sound ominous, but Jupiter is far away. Its belts pose no threat to us. They are a distant spectacle we can safely observe. Thanks to probes like Galileo and Juno, we can turn invisible forces into images and discoveries that inspire wonder more than fear. So when you picture Jupiter, think beyond the clouds and Great Red Spot. Imagine an invisible giant powerful enough to sculpt space itself, dangerous, magnificent, and essential to our understanding of worlds. When people think of Jupiter, they picture danger storms larger than Earth radiation belts that could fry a spacecraft, a magnetosphere stretching millions of kilometers. But Jupiter is not only a menace, it is also a protector. In many ways, we owe our survival to this giant. Its gravity is immense, with a mass 2.5 times greater than all the other planets combined. That influence has shaped the solar system, tugging on asteroids, comets, and even planets. Billions of years ago, it disrupted the region between Mars and itself, preventing a planet from forming there. Instead, that zone became the asteroid belt. Some asteroids remain stable, while others are nudged onto new paths, sometimes crossing Earth's. But Jupiter also shields us. Long-period comets drifting inward are often slingshotted back out after a close pass. Without Jupiter, Earth might have faced far more catastrophic impacts. Astronomers call it the cosmic vacuum cleaner, sweeping debris that might otherwise bombard the inner planets. In 1994, comet Shoemaker-Levy 9 proved this role. Captured by Jupiter's gravity, its fragments slammed into the planet with the force of millions of nuclear bombs, leaving scars larger than Earth. Had it continued inward, it could have crossed Earth's path. Instead, Jupiter absorbed the blow. The planet is not always gentle. Its gravity can also destabilize orbits, sending objects our way. Jupiter is a double-edged sword, sometimes shield, sometimes threat. Yet overall, the balance favors safety. Earth's long stability may not have been possible without Jupiter's presence. Its pull also influences the orbits of Mars, Earth, and Venus, helping keep them steady. Without that stabilizing force, Earth's climate might have swung wildly, making the rise of life uncertain. Think of Jupiter not just as a planet, but as a sentinel. Beyond it lies a reservoir of icy bodies. Most that wander inward never pass the giant. It bends them, catches them, or hurls them away, shielding the fragile blue world we call home. The irony is clear. A planet whose storms and radiation could kill us in hours may also have saved us for billions of years. Destructive yet nurturing. So if you see Jupiter shining bright in the night sky, remember its role. Without it, Earth's story might have been far shorter. The solar system without Jupiter would be less violent in some ways, but far more dangerous in others. Jupiter is not only the giant of the solar system, it is its guardian, its architect, and in many ways its unsung hero. Among the giants of the solar system, Uranus is the quietest at first glance. Through a small telescope, it appears as a pale aquamarine dot, unremarkable beside Jupiter's stripes or Saturn's rings. Yet Voyager 2 and Hubble revealed it as a planet that breaks the rules. Unlike Earth with its 23-degree tilt or Mars at 25, Uranus leans 97 degrees essentially on its side. It orbits the Sun like a toppled spinning top. The result is extreme seasons. During solstice, one pole faces the Sun continuously for 42 years, while the other remains in darkness just as long. Only at equinox does Uranus see something resembling a normal day-night cycle. This tilt reshapes its climate. Its atmosphere of hydrogen, helium, and methane produces winds up to 900 kilometers per hour. Decades of uneven heating create weather patterns unlike anywhere else. Methane clouds drift and sometimes flash as bright storms, but they fade quickly, leaving the planet's face strangely blank. Scientists still debate how Uranus ended up this way. The leading idea is a colossal collision billions of years ago, with a planet-sized body knocking it over. Evidence lingers in its tilted moons and unusual magnetic field. While Jupiter displays storms and Saturn flaunts rings, Uranus is quiet but peculiar. Its tilt alone rewrites planetary behavior. Circling the Sun once every 84 years, each season lasts more than 2 decades. Generations could live and die under a single unchanging sky. Voyager 2 remains the only spacecraft to visit flying by in 1986 during solstice. One pole glowed in steady light while the other hid in shadow. From Earth, Uranus looked bland, but Voyager detected a dynamic atmosphere beneath the calm. Later telescopes confirmed it. Uranus is not dead. Its seasons are slow, but its climate still stirs. Uranus is the planet of long waits and long shadows. With 42 years of daylight, 42 years of night, it is the strangest spinner in the solar system, a world where time itself feels different. If Uranus's tilt bends our idea of day and night, what lies beneath its clouds bends imagination further. Outwardly it looks plain a pale blue-green globe, but beneath is a world of crushing pressure heat and exotic chemistry. Scientists think Uranus has a rocky core slightly smaller than Earth. Above it lies a mantle unlike anything here, a slushy, superheated mix of water, ammonia, and methane reaching 5,000 degrees hotter than the Sun's surface. Under such pressure, methane molecules are torn apart. Carbon atoms are forced together into diamonds which then fall like rain through the mantle. Some grains may be tiny, others boulders. Laboratory experiments on Earth using lasers to simulate these conditions confirm that methane can indeed form diamond structures. Diamond rain is not fantasy, it is likely real. These crystals may sink all the way to the core building thick layers or even oceans of liquid carbon topped with floating bergs of solid diamond. Imagine seas of molten diamond glittering in the dark. Beyond the spectacle, this process may explain Uranus's unusual chill. Unlike Neptune, which radiates excess heat, Uranus is colder than expected. Diamond rain could be carrying heat deeper, trapping it, and leaving the outer layers cool. This hidden ocean of exotic fluids may also shape Uranus's magnetic field. Unlike Earth's, which arises in the core, Uranus's magnetism seems to originate in the mantle, where conductive slurries circulate chaotically. Diamond storms and strange chemistry may be tied to its skewed magnetic field and tilted spin. To us, Uranus is fantastical. To the planet, it is normal physics obeyed in ways we are just learning to understand. So when you picture Uranus, don't see only a calm turquoise globe. Imagine chaos within oceans, hotter than firestorms of falling diamonds, and a mantle that defies our categories of solid, liquid, or gas. The universe holds beauty, but also wonder, and sometimes that wonder glitters as diamonds falling endlessly into the dark. From a distance, Uranus looks plain, but Voyager 2 and Hubble revealed it has rings of its own nothing like Saturn's bright bands. Uranus's rings are narrow, faint, and dark as if etched in charcoal. 13 have been identified, most only a few kilometres wide. They reflect just 2% of sunlight darker than asphalt after rain. They are made mostly of water ice mixed with radiation-darkened organics. Some may be fragments of shattered moons, others the debris of ancient collisions. Whatever their origin, the rings are fragile and temporary. Over time, particles drift, collide, and fall. Even faint, the rings show complexity. Some are sharp-edged, others braided or twisted. Tiny shepherd moons, just tens of kilometres across, tug at them, keeping the structures intact. Without those guardians, the rings would disperse. But Uranus's strangeness goes deeper. Its magnetic field is profoundly misaligned. On Earth, the magnetic poles tilt about 11 degrees from the rotation axis. On Uranus, the tilt is nearly 60. Even stranger, the magnetic centre is shifted far from the planet's centre, leaving the field lopsided. The result is a magnetosphere that twists in bizarre ways. As Uranus rolls in its orbit, the tilted field rolls with it. The magnetic tail, stretched by the solar wind, corkscrews millions of kilometres behind the planet like a twisted ribbon. This makes Uranus one of the hardest planets to model. Scientists suspect the field arises not in the core, but in the mantle where conductive water, ammonia and methane circulate chaotically. That shallow dynamo could explain the offset and tilt. But with only Voyager 2's flyby data, the mystery remains. Picture Uranus drifting in the dark, pale rings, faint against space surrounded by a distorted magnetic bubble. From the night side, its invisible tail writhes outward, unseen but real. Its tilt brings seasons longer than a lifetime. Its mantle may rain diamonds. Its rings are faint shadows. Its magnetic field is crooked and alive with currents. Uranus refuses symmetry, and in that refusal lies its beauty. Not all worlds follow neat patterns. Some tilt, some twist, some rain gemstones. Uranus shows that oddity can be as mesmerizing as grandeur. Neptune's story begins not with a telescope but with mathematics. In the early 1800s, astronomers noticed Uranus's orbit did not match predictions. Something unseen was tugging at it. Two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, worked independently calculating where this hidden world might be. In 1846, Johann Galle turned his telescope to the predicted spot. Within an hour, Neptune was found less than a degree from where the math had said. It was the first planet discovered by calculation, a triumph of reason. Far beyond Saturn and Uranus, Neptune circles the Sun at 30 astronomical units, about 4.5 billion kilometers away. It takes 165 Earth years to complete one orbit. Since discovery, it has barely finished a single trip. Its diameter is nearly 4 times Earth's, and like Uranus, it is an ice giant of hydrogen, helium, and a mantle of water, ammonia, and methane. Methane gives Neptune its striking deep blue colour, more vivid than Uranus's greenish tone. Through a telescope, it shines like a jewel in the dark. Despite its distance, Neptune is not quiet. Voyager 2, the only spacecraft ever to visit, flew past in 1989. It revealed a world alive with activity, massive storms, high clouds, and the fastest winds in the solar system. Ironically, the most distant planet, where sunlight is 900 times weaker than on Earth, has the fiercest weather. Neptune proves distance does not mean stillness. The farther you go, the more violent the atmosphere can be. And it all began because mathematicians trusted their numbers. Without them, Neptune might have remained hidden for decades. Its discovery was a victory for astronomy and for imagination. Voyager 2's 1989 flyby revealed Neptune as anything but quiet. Its cameras captured storms rivaling Earth in size, and winds faster than sound, over 2,000 kilometers per hour, the fastest in the solar system. The Great Dark Spot, similar in form to Jupiter's red spot, was larger than Earth but short-lived. By the time Hubble observed a few years later, it had vanished, replaced by other dark ovals. Neptune storms appear and fade within years or decades, transient and violent. How does a planet so distant, with sunlight 900 times weaker than Earth's, generate such ferocity? Unlike Uranus, which radiates little heat, Neptune emits nearly twice as much energy as it receives. That hidden heat may drive its atmosphere, though why Uranus and Neptune differ remains a puzzle. Perhaps Neptune retains more heat from formation, or processes like convection, or diamond rains stir its mantle. For perspective, standing in Neptune's upper atmosphere, winds would scream past faster than bullets, methane ice clouds racing by under a distant sun shining like a bright star. Lightning may flash below, lighting the darkness. Neptune also has extreme seasons. With a 28-degree tilt similar to Earth's, each season lasts over 40 years. Currently, the southern hemisphere is in spring brightening over decades. Seasons unfold not in months, but across generations. Bright methane ice clouds add to the drama, drifting thousands of kilometers and casting shadows. They appear near storms, then fade like brushstrokes wiped from a canvas. Neptune's faint rings also break rules. Arcs of material that physics says should disperse remain stubbornly clumped, perhaps held by a moon's gravity. Its weather is often localized. Dark spots migrate across hemispheres, while bright clouds trail behind as though the planet breathes in colossal rhythms. Each storm hints at secrets of the deep interior, but vanishes before scientists can decode it. The energy balance remains unsolved. Some propose Neptune's atmosphere converts heat into motion with extraordinary efficiency. Others suggest methane helps trap and release energy. Still others suspect unknown physics in its mantle. Neptune humbles us. Earth and Jupiter taught one kind of weather, but Neptune shows another: winds without limits, storms without warning, seasons that span lifetimes, and a hidden furnace that keeps the machine alive. At the edge of the solar system, far and cold, Neptune is fierce, restless, and alive. Neptune may be known for storms, but its rings tell another story, subtle and shadowy. Unlike Saturn's bright bands, Neptune's rings are faint and dark, made of dust and icy particles coated with radiation-darkened material. Detected in 1984 and confirmed by Voyager 2 in 1989, they reflect little light. The outermost, the Adam's ring, holds bright arcs, clumps of material that refuse to spread out, despite orbital mechanics predicting they should. Scientists think the nearby moon Galatea corrals them, but how the arcs remain so sharply defined is still debated. Closer in lie the Leverrier-Lassell and Gall rings, likely formed from collisions between small moons. Yet Neptune's largest moon, Triton, steals the stage. Discovered weeks after Neptune in 1846, it orbits backward, a retrograde orbit implying it was captured, perhaps a Kuiper Belt dwarf planet, pulled in by Neptune's gravity. Its tilted path and reshaped surface support the theory. The capture may have destroyed Neptune's original moons, their debris helping form the current rings. Voyager 2's 1989 flyby revealed Triton as geologically active. Instead of a frozen relic, it showed cantaloupe terrain, smooth plains, and nitrogen geysers erupting kilometers high. At 235 hours, such activity was shocking. Sunlight, weak but steady, may heat transparent nitrogen ice enough to trigger eruptions, leaving dark streaks on the surface. Even in deep cold, Triton is alive. Triton's future is dramatic. It is slowly spiraling inward. In about 100 million years, it will cross Neptune's Roche limit, where tidal forces will tear it apart. The fragments may form new rings, possibly brighter and more massive than Saturn's. For now, Triton circles backward, restless but intact. Together, Neptune's faint rings and Triton's strange orbit tell a story of capture and change. The planet discovered through mathematics is remote and dim, yet alive, with winds' arcs and a stolen moon destined one day to fall. Neptune remains a place of storms, fragile beauty and mysteries still locked beneath its blue haze. We've journeyed far tonight. From Cassini's birth to its final dive across Jupiter's painted storms, Uranus's decades of day and night, and Neptune's fierce winds. We've lived a spacecraft's lifetime and imagined rains that never melt, and yet much remains hidden. Saturn still conceals the true length of its day, cloaked by a magnetic field theory says should not exist. Its auroras sometimes blaze without the sun's touch, as if powered from within. And deep below Uranus's clouds, diamonds may fall in silence, forming oceans no one has seen. These mysteries remain unanswered on purpose, leaving space for curiosity to call us back again. Now as you settle into rest, let's breathe together. Inhale for 4, hold for 7, exhale for 8. Again, 4, 7, 8. Let your body grow heavy and your mind drift as our spacecraft once drifted through rings and storms. Good night. May your dreams carry you to strange worlds and quiet wonders. When you wake, tell me which mystery should we explore next. Leave your thoughts, and together we'll choose where to travel. For now, close your eyes. The universe will keep spinning and the planets will keep whispering their secrets. Sleep well.